Okay, hi. Today is Friday the 13th, and we're here. And if there are any additional other homeworks to turn in, you should turn in. Do you have homework to turn in? Good. So, why don't you, let me, right, you don't want to walk in front of the camera because then they'll think that actually real human beings are taking this class and we don't need to get, okay, even though they can't read it at this distance. And this is, you also have the copy of homework number 1 if you want that back. Okay. Okay, that looks good. All right, what I'd like to do first of all is go over homework number 2, and it looks like we're making progress on getting the additional homework number 1 back. Homework number 2 was first of all to fit this least squares. If we can, thank you. So it was to fit this data using least squares. And this can be done in a variety of different ways, either by using a program that you buy, or by actually programming it, or by doing it on a spreadsheet, or a number of hand calculators like mine will actually do this. Although I never use it to do this, and now I push too many buttons on my hand calculator and it keeps saying program, and I don't know how to eliminate that. So I have to find the instruction booklet. Although it's adding and dividing and multiplying, it says funny things which seem to upset me a little bit. So the results that I found for this were that y equals 3.215652 times x minus 60.74609. And I also fit this, so this was the least squares. Let me pan back here, get a little more room. This was the least squares fit. And just for fun, I also fit this data by using this nonparametric method that I had mentioned, the Hodgson-Lehmann estimator. When I did that, I actually got y equals 3.13571414x minus 58. So this gives you a feeling for the difference of the parametric and non-parametric fits. The errors in the least square fit in the slope using the formula that I told you to use are plus or minus 0.543, and in the intercept plus and minus 36.35 for the standard deviations of the errors. So they're actually pretty big. And the R value is 0.863235, and so R squared is about 0.745. So this means that the data is pretty tight, and about 3/4 of the variation, 75%, is explained by the fit. And this was fitting the weight versus the height, where y was the weight and x was the height. Now, the second part of this problem was to fit this the reverse way, where we do a fit, keep it in the same corner here, where we plot height versus weight. So this is now y, and this is x, and this is the other regression. And in this case, I got y equals 0.231733x plus 31.10778. And that was for the least squares fit. And for the Hodgson-Lehmann fit, the non-parametric fit, I got y equals 0.2264957 times x plus 32.92308. So the error in the x, according to least squares, is 0.039, and the error in the intercept is 32.92308. And the R value is 0.8632345, and R squared equals 0.745. Now you'll notice this is exactly the same R value as we had when we did the other fit, the other regression. And in fact, this is what always happens, that R is independent of whether we fit y on x or x on y. because the way R is determined has to do with the goodness of fit, and so isn't affected by whether we do one on the other. And it looks like I didn't bring my plot here, but bringing someone else's plot, which looks nice, and seems to have roughly the same numbers that I have. 60, x is 31, and 2. So this looks right. And so this shows you the two different lines, so this is done nicely. And we can see here, again, that the two different lines are not exactly the same. And here, this is an example. We might expect the error in this coordinate, this variable, is roughly the same as the error in this variable. And so there's no real a priori reason to choose one or the other. And we can see that, again, the assumption of where the error is changes the slope of the line. And you should really understand this, that when we're fitting least squares, we have some give based on what the assumptions in the method are. So neither of these lines is more correct than the other. It just depends what we're doing. And I also have a program in Basic, not C, that does this fit. And I am shuffling papers off camera, which you luckily can't see. And I just wanted to make one point about the program. First of all, it's relatively simple. And one of the things that I've done here is I've actually, although it doesn't say here, what I usually do is make it double precision, because this program in calculating things, and here these are double precision, and then they're set equal to single precision numbers. As I mentioned once before, this procedure of calculating all these squares uses up a lot of significant digits. And so it's useful to run this program at slightly higher than usual numbers of decimal places. And in the 6 decimal places or 5, whatever I have in simple basic, you can get slopes or intercept that differ in the 3rd decimal place if you don't do this. So this calculation is somewhat sensitive to the numbers, and it's useful to do this with a little higher precision. Does anyone have any questions on the homework? Okay. What I'd like to do today is discuss a number of different things, actually. So let me start off by a problem that's already come up, which is in the homework that you already did, we had a frequency distribution, number versus whatever it was. What was it? It was just data, was it? I don't remember whether it was heights, values. And we had these bins that you all quite successfully fit with a Gaussian by using the mean and the standard deviation to fit the Gaussian. And a reasonable question to ask is, first of all, how come I can't draw straight lines? But a second reasonable question might be, is this a good fit? Is this Gaussian a good fit to this data? And this is different than the question we had before. In the situation we had before, we were fitting a functional form to data. So here we were fitting some functional form to data, but we weren't fitting a distribution. Now we're fitting a distribution function to the data. And mathematically, it turns out this is a different problem. And how we handle this problem is different than how we handle this problem. Okay? The least squares can find us the maximum probability of getting the right distribution, but how we tell whether the distribution is the correct one is a little bit different than how we tell this is correct. So one of the ways to handle this is something called a chi-square test. So I'll describe that. And in the homework that you're given next, you'll be able to in the next homework, you can use the data from the first homework and actually do a chi-square test and tell me whether the Gaussian that you fit is any good or not. So let me go over chi-square. It's spelled this way. And in Greek, and probably in original Greek, all the C's are hard C's, so it's chi squared and not chi squared. And it's usually represented by the Greek letter chi squared. And what this is, as I said, this is a test to tell if a distribution, which we've been calling probability density functions, really fits a set of data. And what we do in this test is we have the observed frequencies. I'll let O equal the observed frequencies in the data. So these are the number of events typically in each bin that we have in the histogram. So again, if we have our histogram, this is definitely not a straight line date. So for example, in this bin, there are 37 events. That O would be 37. And then we can compute what E, the expected frequency, is from the theory or the fit. And for example, for this particular bin, it might have been 38, for example. And then what we do, the value of chi squared is equal to, in the first bin, the observed minus the effective frequency squared divided by the expected frequency plus the observed minus the expected frequency in the second bin divided by the expected frequency, etc., all the way up to the, let's say, k bins squared divided by the expected frequency in k. Now, one of the things you have to realize when you do this, we've partitioned the data into a number of bins. So we can't do it for each element of the data separately. We do it for bunches of data together. And that's one important aspect in doing a chi-square test. So again, we have to make these bins reasonable. They have to include enough data, but not so much data that we have no bins. So it's very important that we're dealing with bins and the frequency, that is the number of data points within each bin. So this is a different problem than fitting a line through a bunch of data points. The data are grouped together. And now, as a part of this chi-square, we have an element in it which is called the number of degrees of freedom, sometimes represented by nu. This is a Greek letter nu, as opposed to a Yiddish nu, which means something else, I guess. So this is equal to k, which is, you can see over here, was the number of bins that we had. So it's equal to k, which is the number of bins. And typically, the number of degrees of freedom depend on how much data we have. It's typically the data minus the number of constraints that we put on the data. So we have these number of bins minus 1. The reason why it's minus 1 is because if I tell you all of the number of data in the n minus 1 bins, by subtracting from the total, you can know how much is in the last bin. So we put a constraint on this in the way we put things into bins. Minus m, where m is the number of parameters needed in the fit. So in our case, in fitting the distribution, we've used two parameters, which are the mean and the standard deviation. So in this case, nu will be the number of bins, k, minus 1, minus 2. I think that's right. Since I don't have the answer to the problem with me, I'm presuming that's right, that the number of parameters needed in the fit is 2. So you can go back on the chi-square, and then in the back of your book there are tables, or on your computer there are tables given chi-square and nu to get a probability value. And I'm going to explain how we interpret these probability values today. So I'm doing my usual thing, apparently, of defining things after I use them. So I'm going to continue to do that today, at least for a little bit. And the reason in this case is historical, because I didn't discuss chi-squares at this point. I discussed it after I defined the probability. But I thought it would be useful to discuss it now in terms of these statistical tests. So that's why I'm doing it first here. Okay. So that's a chi-square test. Okay. What I'd like to do today is to discuss a little bit about errors in measurement. And first of all, one, how do we describe or handle errors? Two, how do they propagate through measurements? That is, let's say we have some quantity which I call A. And that's some function of actually B and C. And if I measure B and C, from those measurements, what is the error in A? And I'll discuss how we do that. And then after that, in the second part today, what I'll describe a little bit is hypothesis testing and these p-values that I alluded to a little while ago. Okay. So let me start at the beginning of how we describe errors in an experiment. Let's say we have a Gaussian distribution, so we have data. So we've looked at the number of times a particular value appears in the experiment. And let's say this has a normal Gaussian distribution. Now, let's say we repeat the experiment a number of times. So every time we repeat the experiment, we'll get a slightly different distribution. So maybe this is what happens when we repeat the experiment the second time, and this is what we get when we repeat the experiment the third time. So every time we repeat the experiment, let's say this is the mean this time, and this is the mean this time, and this is the mean this time. Every time we'll get a slightly different mean. What we would like to know is if we take the mean of the means, or we combine the data in some way, what is the best guess, or what is the range in which the real right value of the data should be? And this is called the standard error of the mean. And it's usually abbreviated SEM, which as far as I know is still lowercase, although all these things seem to be changing from lower to uppercase on me. And this is not the same as the standard deviation, because the standard deviation, remember, is the widths of these curves. And so this is a different measure. And what this is equal to is that the standard error of the mean, SEM, is typically equal to the standard deviation divided by the square root of the number of measurements, even if we only have one set of measurements. So let me say this again. Let me say if the problem is that we've done one set of measurements, so we have numbers versus a value, and we get only one Gaussian curve, and let's say its mean is here, and we'll call that M. What we'd really like to know is M plus and minus some value that brackets what the real values of M could be. And this quantity is called the standard error of the mean. So this is the range around which is the real value, whatever that means, a right value, of m, of the quantity being measured, of the data. Now, sometimes people report measurements like this. They report measurements of the mean plus and minus the standard deviation, where this is the standard deviation. This is crazy. This is really stupid. 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 Because we've just seen that the SEM equals sigma divided by the square root of the number of measurements. And so, depending on how many measurements we have, this may actually be a very, maybe a much larger number than this. And what we really want is the range of the errors of the real values. So when we talk of the real values, we should always plot SEM, give the SEM, and not the standard deviation. Because the standard deviation tells the spread in the amount of measurements, but it doesn't tell you what the error is away from those measurements. And that's the quantity we really want. So for example, when we do a plot of measurements, let's say this is some value, again, of height versus weight or something. And we have data points, and we want to plot the error bars on the data points that correspond to the errors in the measurement. We should always use error bars that are the values of the standard error of the mean. And people who plot standard deviation here basically have no idea what they're doing because the standard deviation doesn't mean anything here. What we really want to know is what is the real range of values that compared to the correct values, and that's provided by this measurement of the standard error of the mean. And it's not, as I said, it's not equal to it's equal to the variance divided by the square root of n. So if you plot standard deviation here, you don't know what n is, and you don't know whether things are really large or small. So it's really common amongst people who don't know what they're doing. I mean, I think amongst people who know what they're doing, almost always plot SEM. I always plot SEM. But I don't always know what I'm doing. So I think this is a very important point, and this is also a good test. As I said last time, we actually with the people I was with last week, we were looking at some data on some plot that had a linear plot and a curved plot on it, and you couldn't tell anything. It should have been on a semi-log plot because they thought this thing was single exponentials. So if you remember, the lesson we had last time was you always plot things on graphs to make them straight lines, and because the straight lines are the only things you can see in a plot. And so that's one crucial lesson. And another crucial lesson here is that you should always plot SEMs. And usually people who don't plot SEMs, that's at least a warning sign in the same way that plotting a very curved plot is, instead of using the appropriate axis, is a sign that something is up. These people don't exactly understand why they're doing things. Remember, we're using plots and data and parameters and all these statistics to tell us something. So that means you need to use the right statistics that's the most meaningful. And in this case, the SEM, which is the real range over which we think the correct value is very important. And it's very important. It even says in my notes here, see, crucial in words that are big enough even to read. So it's not in red because this was Xeroxed from last year's notes, but you can see it's still, it may have even originally been in red. Okay. So, so we're generating a bunch of clues when you read articles to see whether people know what they're talking about or don't. So you already have this clue about the graphs. We have the clue that you should look for SEMs in the abstract and in the boundaries of the graphs. Now let's discuss, are there any questions about that? Yeah.
Well, how do you figure it out?
Oh, okay. Again, the way you figure it out, let's say you had one set of data. So I'll just repeat it. You have one set of data, and you calculate from that data the standard deviation. And then this SEM is equal to the standard deviation divided by the square root of n, where n are the number of measurements in that data set.
Right, but I mean, like say you have the thing, the height is at 10.
Right.
So, and your SEM number is 5.
Okay. In terms of doing it on this plot, or in terms
Yeah.
of, okay. In terms of doing it on this plot, what I have meant by this graph is that this data point really represents the mean of a number of different measurements. let's say in this case it was 10. Okay, so this point, let me call it y and x for the moment. This point was plotted really using 10 measurements. And then the value of the center is equal to the value of the mean of the measurements. And then typically what I would probably do is, I guess, what would I do? In fact, I don't know what I do because I give it to a program. So probably it plots one SEM up and probably one SEM down from that measurement. Well, we're going to see a little bit throughout today how to interpret the lengths of these bars. So we're going to see a little bit more about this later.
But so if the SEM was, say, 2,
Right.
then you'd go,
Yeah.
the bottom one would be at 8 and the top one would be at 12.
Yeah. So let's give some specific values. If the mean was 10 and the SEM was 2, then this would extend up from 12 and down to 8. Sometimes people, for reasons we'll see in a moment, plot 2 times the SEM. I think I usually plot the SEM 1 times the SEM. But we'll see what the meaning is. Because the real question is, let's say we have 2 data points. We do 2 measurements. And we have this, and we have another one here. And then these are kind of close, and they're overlapping. And we're going to try to decide by the size of these bars whether this is really the same as that. So that's what we're going to do today. If we get far enough, unless I keep saying the same lines over and over again about lowercase and everything else. So we'll see how far we get. Okay? So, are there any other questions on this? Okay, good. So, let's now discuss a little bit how do errors propagate. And I don't think this is covered. I don't remember if this is covered in Spiegel or not. I don't think it is, but I don't remember. It may be. Let's look at some function f of x and y. And let's look at small deviations or errors in this function f of x of y. So we'll call these small errors delta. So this is a Greek delta, a lowercase delta instead of an uppercase delta, because apparently this is like a lowercase Friday, so everything is going to be lowercase. And let's say, let's call delta the difference between the values of f and the average value of x, which I'll denote by a bar over f, which is one way to denote an average. What is this equal to? Well, from the Taylor theorem, a Taylor expansion, this is equal to the partial derivative of f with respect to the first variable x times the difference in the x value, which is xi minus the mean, plus the partial of f with respect to y times y minus yi minus the mean value of y, because this is the deviation in x and this is the distance in y from a Taylor expansion from the first derivative. And the next terms would have higher derivatives. But since we're not into higher order things, we'll throw away all those derivatives. So that went pretty fast, right? I just jumped into the partial derivatives. Okay, so really what this is, we're going to call this the error or the small change in y, and we'll call this a small change in x, and we'll call this a small change in y. So now I can write this equation again as the small changes in the function are equal to the partial derivative of the function times the changes in x, plus the partial derivative of the function with respect to the changes in y. So now, let's say for the first example, I have a function f of xy, which is equal to x plus y. And let's say I want to measure x and y, and from that compute the function f. So what I find here now, if I carry, yeah.
Y is above the y minus y I yes minus
Y bar, which is the
y. Didn't you put an I 2 there?
no, we can kill that I.
Okay.
It's gone. Okay, good. Sorry. So now if I compute the f dx here, that's equal to 1, and the f dy is equal to 1. So that means that the error in f is equal to the error in x plus the error in y. So all it means is that the errors add. Okay? So when I compute the value of f, the error in the computation of f, if f equals x plus y, is equal to the error in x plus the error in y. Okay? So that's the first example. And I'll keep this on the page. Let me give now a second example. Second example is, let's say f of x of y equals x times y cubed. So now let's do the same business again. And now the x equals y cubed, the f dy equals 3y squared. And if I now do delta f, it's equal to y cubed times delta x plus 3y squared times delta y. This is sort of a funny form. I mean, emphasizing that very often, I haven't been emphasizing, but by writing things in different forms, sometimes we can see different meanings. So let me write this in a slightly different form. Let me divide both sides by f. And f is also equal to xy cubed. So if I divide this by the same amount, I'm OK. So this is delta f over f equals delta x over x, because everything else cancels, plus 3 times delta y over y. So what this says now is that when we have an exponent, remember here we had f equals x times y cubed. The way the errors propagate when we have something cubed with an exponent is that the fractional errors, which is the error divided by the amount, and this is the error divided by the amount, the error divided by the amount, are proportional to things raised to that exponent. So if I have something that goes like y cubed, then the fractional error will be 3 times this error in y, the fractional error in y. So whenever I have an expression that has a power in it, it means that the final error here will be 3 times, if it's cubed, times the fractional error in y. So if I'm evaluating an expression and something is raised to a high power, the error in that variable contributes most of the error to f. And the contribution is proportional to the power of the exponent. Is that clear? Okay. So this means that when I have equations, if I have equations like f equals x to the 101st power, that this is a bad thing to evaluate because the fractional error here will be multiplied by 101 times when I evaluate that. So this is kind of a bad experiment to do. On the other hand, this experiment, f equals the 101st root of x, is a good experiment to do because the error here will be very small on whatever the error there is. Okay? So this is good as far as the error propagation goes. This is bad. Bad, sorry. Should have green. I don't have green. Bad is definitely red. And this is green, though it looks like blue. This is good. So this is important to keep in mind when we evaluate expressions from data, or from measuring something else and computing something from the data. When we raise it to a high power, the errors propagate, and they propagate proportional. So the errors, the fractional errors, propagate proportionately to the exponents. And this is something that's good to know. Okay. So the next question is, if this is how the errors propagate, how do they affect the standard deviation, the computation of the standard deviation? And we're going to see, I'm going to use this in a very unusual way. Not very unusual, but in a way that I haven't usually seen done. in deriving the statistical test later. So the point of going through this derivation now is not only to use in and of itself, but I'm going to use this as an argument to justify the reasonableness of the statistical tests that I'm going to derive later. So let's say in this case that we measure how have I done this, x and y, and we're trying to get f, which is some function of x and y. So we know that we'll call s squared the standard deviation, which I'll also call s. S is typically the standard deviation measured from the data, which is from the sample, and the symbol sigma is usually used for that of the population that we're trying to derive from the sample. So let me say this again. We have the sample, which is the data, which we represent by Roman letters S, and from that we're really trying to reach the real values from the population. So these are kind of the real values, and we'll represent that by sigma, and both of these we'll just call standard deviation. So S, the standard deviation squared, is really the sum of the individual deviations in F squared divided by the total number of deviations. So we remember before we used the fact that delta F is delta F xi for each variable times delta xi plus the derivative of F with respect to the y'th coordinate. And I'm putting the yi's here because this is for each data point that we have. And then if we do this sum, s squared, so we take this and I square it in order to get that, I get a series of terms that are 1 over n times something like the sum over I of df dx evaluated at xi squared times delta xi plus the other term, which is, so this sum is over everything. Let me write the sum separately. The sum df dy I times delta I squared plus the sum over I of df dxi, maybe times 2, df dyi, delta xi, delta yi. Now, this term, if the errors in x are independent of the errors in y, then sometimes this will be positive and this will be negative, and sometimes this will be negative and this will be negative, and positive and negative. So we'll get all combinations of signs here. And that means that overall this cross term will approach 0, so it doesn't count. Okay, do I need to say that, more words about that? This is sort of a typical situation where when we multiply two independent errors, the average of those should be 0, because sometimes one is greater than 0 and sometimes the other one is greater than 0. So they take on all possible random values, and so we get a series of numbers here that are plus and minus, and so they sum approximately to 0. So that means now we can look at what this means. And let's see again what those two terms means. It means the standard deviation squared in S equals, I'll keep the first term, if I take the summation here that goes through this first term, it means the f dx squared times sx squared, because this divided by n with the summation sign is just the standard error in x, and the second term is just the standard error in y. So I could have done that a little more cleanly, but it's not too bad. Okay, so this term is just going to be the derivative squared times the standard deviation in x, and the same thing for the second term. So now we can see, given we evaluate x and y, we now can determine the standard error in the function. So let me give you the following two examples that we had before. Is this okay, or have I done this too fast? Sort of on the edge. Okay, but it's straightforward. All I'm saying is that there's a way of looking at the fluctuations so we can derive what the standard deviation is from the variables that make up the function that we're evaluating, and this is that function. So let me give you an example of how we use this. If the function is f equals x plus y, then as before, df dx is 1, df dy is 1, and so this formula says that the standard deviation of f squared equals sx squared plus sy squared, or to say it differently, that the error we get, the standard deviation in both, is the sums of the squares of the deviations. Well, what's interesting in this is that it's not this. Okay? That the standard deviations don't add so that the standard deviation of each one is not the sum of the other two, but it's the square root of the sums of the squares. So that's what's interesting about this. And we can also do the same business that we did before if the function f equals x times y cubed, and we go through the same business we did before. We'll get f of x squared equals y. In this case, the partial of f with respect to x is y cubed. Partial of f with respect to y is 3y squared times x. So then this is y times sx squared plus 3y squared times x times sy squared. And again, if we do the trick we did last time to give this more interpretive value, if we divide this by f and x y cubed, then we get the relationship that the fractional change in f is equal to the fractional change in x plus 3 times the fractional change in y. So again, the way the standard deviations change when we have to compute something is that if we have an exponent, the fractional change in the standard deviation is proportional to, the square of that is proportional to the exponent. Again, so it's the square of the standard deviation is proportional to the exponent. And again, if this means that we have something raised to a high power, even if we do the measurements good, we still incur a big error in using those measurements to generate the function that we want. In general, if we have more variables, so if I have a function of x1, variable x2, variable x3, etc., up to x to the n variables, then the standard deviation of the combined function is the sum from I equals 1 to n of the f dxi times squared times the variance, standard deviation in each one squared times the square root. And it also turns out that that same is actually true for the population. So this is also true for the population variance. So this is sigma xi squared. And it also is true in how the standard errors of the mean combine. So the I subscript here is a little bit confusing because it's in numbers of variables, not data points. So all three of these things combine with a formula that depends on the squares of the partial derivative of the function times the values of the individual elements. Okay. Are there any questions on this? I'm not so much interested if you understand all the derivations. So what I'm trying to show you is that the derivations, if you can flick to the, maybe to the camera for a moment, if you're there. Yeah, to me, thanks. And come in a little bit tighter. What I'm trying to show in this is how the errors propagate arises in some reasonable way in how we compute them from these partial derivatives. And that leads to these formulas for the standard error, for the standard deviation of the mean in the population and the standard error, and things basically sum in this Pythagorean way that we have the square root of the sums of the partials times the other errors. All right. What I'd like to do next, are there any questions on this? Okay, what I'd like to do next is a very important problem. Maybe if we can go back to the Elmo, maybe I should stick with that because I think I'm going to write. I think it's more important for me to write rather than talk. Let's say we have an experiment. So we have an experiment, and we get a value out of the experiment that I call x. And let's say we want to run a control. And out of that control, we get a value that's c. So these would be numbers. What we'd really like to do is test whether there was an effect of the experimental situation. Or to say it differently, this may turn out to be R, but for the moment it's is A and C different? Where X and C are numbers. That is, we know that when we do an experiment, sometimes we can get numbers just because of these random errors that are a little bit different. And so if sometime we measure 18.5 and the other time we measure 17.8, is this really the same or not? That is, what we really want to ask is the difference between X and C due to chance? Okay? And if it's not due to chance, if this difference is not due to chance, then whatever happened in the experiment means it's real, that there's a real change from the control. Okay. Now, the way we actually do this, it turns out this seems like a pretty straightforward thing to do, but it's kind of hard to do, actually, in terms of the statistics. So, in a certain sense, this is the question we want to answer. Is there a real effect? And we can't quite answer this question directly. So what we really have to do is ask these questions. Is the difference due to chance? If it's not due to chance, then it's a real effect. Which is not the question we really want to ask. The question we really ask, is the effect real? So we're not asking it that way. We're asking, is the difference due to chance? And if it's not due to chance, it's real. And the way we usually do this is to set up what's called a null hypothesis, which is usually abbreviated H subscript 0. And what we want to do is determine the probability that the null hypothesis is true. If this probability is large, well, the null hypothesis will usually be that the difference is due to chance. Okay. So if the probability is large, then the null hypothesis is true. It means that the difference was due to chance, and there's no effect of the experiment. If the probability is small, it means the probability that the null hypothesis is true is small, which we usually call false. The probability is small, it's true, it's false. And this means that the difference is not due to chance and implies that the experiment produced a real effect. The typical probability levels, probability runs from 0 to 1. The typical level we choose as being small or large is 0.05. So everything between 0 and 0.05 is small, and everything between 0.05 and 1 is large. And we'll discuss a little bit why we chose this value of 0.05. So this is how we go. What we're going to do is determine from the data these p-values, these probability values are very often represented, again, by the lowercase letter p. And if p is greater than 0.05, then the null hypothesis is going to be true. and there's no effect in the experiment. If the p-value is less than 0.05, the null hypothesis that there's no difference, or the difference is due to chance, will be false, and the experiment had an effect. So we're hoping we get low p-values typically in how we do this. Let me give you an example of some numbers, because I think this is a very, very confusing concept. At least it was very, very confusing to me. Actually, it was very, very, very confusing to me. So it's 3 varies. So 3 varies is either more or less than 3 reallys, I think. So let me give an example with some numbers so you get a feeling for this. Let's say in the experiment, the value that we measured was 10. And let's say the control value measured in the experiment was 12. And let's say what we're looking at, for example, I can make it specific, but we don't need to make it specific. Let's say from some statistical test, which I'm going to show you how to compute in a little while, the p-value that this difference is due to chance is 0.1. So that's the probability that the difference is due to chance, is 0.1. So what we would conclude here is that the difference is due to chance, and so there's no effect in the experiment. And this might contrast, for example, where the experimental value is 2, and the control value equals 12 again, and the probability might be between 0.02 that the difference is due to chance. And so we do have an effect of the experimental condition. Well, no, this probability is 0.02 that the difference is due to chance. Since this probability is so small, we conclude that it is not due to chance. And these are how p-values are used in experiments and how they're reported in the literature.
Shouldn't it be smaller than
0.05, where? In this case,
0.01?
well, in this case, we're,
0.05, okay.
right, in this case, this is less than greater than 0.05, okay?
I thought it was 0.01.
Okay. Let me discuss a little bit of what this point, let's discuss a little why we choose 0.05 and what it means. In psychology, this is sometimes called the alpha level. First of all, let me, instead of discussing why, let me discuss what. What does this mean? Let's say this 0.05, so let me do a blazingly rapid calculation. 0.05 is equal to 1 over 20. Okay. What this means is that if I do an experiment 20 times, okay, I run the same experiment 20 times, and there's no difference, I know, between the experiment and control, 1 out of 20 times, I'll get a statistically significant probability. Again, what this p-value means is how often something is due to chance. And if it's due to chance 0.05% of the 0.05 of the time, then 1 out of 20 times when I do this, I'll get what looks like to be a positive result. So there's nothing magic about this level. This means that we're going to say, how often do I have to redo this? So it's unlikely the difference is due to chance. But we can't say when it's real. We can only say how often that is. So think about it again. What you're not allowed to do is run the experiment 20 different times or run 20 experiments and pick out one of them that work, because that has to happen. Another way to think about this is that 1 out of 20 times the experimental result is due not to the effect that it's real, but the fact that it was due to chance. So if you picture a bookshelf full of books, you should take out 1/20th of them, or 5% of them, if they published articles at the 5% level, because 1/20th of them are meaningless. They just happen by chance. Okay? So we can't tell when the result is real. All we can tell is how likely that difference would be produced by chance, and we can use this level because 1 out of 20 seems about right. If it was, I can say it historically, what people wanted to do was to set a level, so let's discuss a little bit why it's 0.05. Historically, it seemed more sense to set this level at something like 0.001, which is 1 out of 1,000 times. And that's what people did at the beginning. Except it was very hard to get good results. This never happened, no matter how well you did the experiment, because it's very hard to get something to this level of accuracy. And the problem here is that we've made this criteria too stringent. And sometimes, that is, we will accept the null hypothesis because it didn't reach this level of significance when we should have rejected it. And this is called a false negative, because it says that the difference is due to chance, that there's no effect, so it's negative, but it's a false negative. There really is an effect. This is also called a type 2 error, Roman number 2. So if we make this criteria too stringent, we'll never get statistical accuracy because we have to do the experiment too well or too often. But it's not just that. It's that we run the errors of getting a false negative. And the same thing happens if we set the level too high. So if we set this test level, for example, at 0.2, this means sometimes we'll get a result. That is, we'll think H0 should be accepted when actually we really should reject it. And this is called a false positive, or a type 2 error, a type 1 error. So we have to pick this level, if this is the alpha level, and we set it at 0.05. If we pick it too low, then we'll get false negatives. And if we pick it too high, we'll get false positives. So we pick it at 0.05 as a reasonable compromise of this. This is also related to something called the power of a test, or operating characteristic curves. Which tells us how many type 1 and type 2 errors happen. When I'm more cynical about this, I think we pick 0.05 because we're too lazy to do enough experiments to get it more accurate. But someone has also given me this argument about the relationship of the power in type 1 and type 2 errors. There are ways of maximizing type 1 with respect to type 2 errors, which are based on something called the Neiman-Pearson lemma, which I'm still upset about because I think if I would have answered that one additional question right, I would have passed the second actuary test, and I might have wound up to be an actuary, so I might not have been here. So I'm very sensitive to this, or mildly sensitive to this. Okay. But it is interesting that historically, people pick this level at 0.001 because they wanted to make sure things are really true. And we don't pick that level. We're willing to settle 1 out of 20 times. So now let's see how we calculate these p-values. So how do we calculate these p-values from data? So let's say I had an experiment where I have a mean minus a standard error of the mean, because that's what I've been telling you we really want to use. And let's say those values from an experiment were actually 5.13 plus and minus 1, sorry, what I have in my notes is 5.3 plus and minus 1.2. So this is the mean minus the standard deviation from an experiment. And the null hypothesis, again, in this case, is, or let's say I know in some way that I'm not going to tell you, that I know that the true mean for this data, the real mean, should be 6.0. And I just know that. Because maybe this was like a coin flip experiment where I know in principle what it should be. I have some way of knowing what the true mean was. So what I'm trying to find out, the null hypothesis would be that 5.3 is not different from 6.0. In other words, that the difference between 5.3 and 6.0 is due to chance. And if the p-value is high, then we're going to accept this null hypothesis, which means the 5.3 is not different from 6. And if the p-value is low, means we're going to reject this null hypothesis, and the 5.3 is, we'll accept null hypothesis, 5.3 is equal, and we'll reject the null hypothesis and say the 5.3 is really different. Okay, so the question is, how do we calculate this p-value? Well, one way to do it, if we go back to our Gaussian curve, and we had this, but you don't want to go back that closely. We have this z value, which is, in this case, the data minus the theory divided by the standard deviation of the mean. Remember, last time the z value was something like x minus the mean over sigma. Now, in order to make this meaningful, because I said what's meaningful in the data is the deviation from the true value. And in this case, we have the true value in terms of the theory. So what we want is the deviation between our data, which will be the mean from our data, minus the theory divided by the standard deviation. So this is what it was before. We're not going to count it. This is kind of what the z level is. In our case, if the z will put us in some place over here, and what we want to do is determine the probability under this curve greater than that value. That is, what's the probability of getting this deviation or greater? Now, since I have changed the example a little bit in how I set it up originally, we now know that the absolute mean, actually, of the theory was 6, and the value we got was 5.3. Let me change this a little bit to, I tried to fix this in my notes, but it looks like I didn't fix it. So instead of making this 5.3, let's make this 6.7. So what we get from the experiment here is 6.7. What we're trying to find out is what's the probability that we could get 6.7 or higher if the mean is really 6. So I'll say that again, is what is the probability of getting 6.7 or higher if the real mean is 6.0. Okay? And so what we do is we look at this value of z, which is, in this case, the data, or the mean of the data minus the theory divided by the SEM. So that's 6.7 divided by 6 divided by 1.2, which works out to be, doesn't say here, works out to be something. And next, we need the probability that the z value, I'll call this z naught, the probability, or zm, for the z of the mean that we measured, the probability that z is greater than that mean turns out to be 0.14. So what does that mean in this case? Does this mean that this number differed from the theory or not?
No, it doesn't. It's a chance.
Right, it means that the change is due to chance, so it's really consistent with that. Now, in general, it's very good to sort of have a feeling for how much these deviations need to be in order for an effect to be real. So I can make this table in two different ways. If I write Zm, I can have the probability that some z is greater than Zm, and I can make the values of the probability even. So at 0.1, 0.05, 0.01, 0.005, 0.0002 correspond to Zm's of 1.3, 1.6, 2.3, 2.6, and 2.9. Or I can make sort of the same table with even values of the Zm and sort of then what the probability of z greater than zm is for those values. So if I make the zm 1.0, 2.0, 3.0, 4.0, 5.0, probabilities are 0.16, 0.02, 0.0013, 3 times 10 to the minus fifth, and 3 times 10 to the minus 7. And these tables are in the Spiegel's book, too. Okay. So kind of now we're getting a sense now that if two numbers were, let's say, about 2 times away from each other, that if the difference between two numbers is 2 times the standard error of the mean, then the deviation is real. We're going to see this in a little more clearly in a moment. But let's say I had two numbers from an experiment, 1.3 plus and minus 0.1, and let's say 2.0 plus and minus 0.2, where these are really the SEM. So now I'm going to tell you how I read articles. So I know that the standard error, if I do a subtraction here, which is 0.7, the whole purpose of doing what I showed you before is that the standard deviation or standard error of the mean should be approximately the square root of this squared plus that squared. So that's going to be a little bit less than 3. So let's say it's about 2.5, just approximately. And if that's about 2.5, if the difference here is 0.7, that means the difference between these two numbers is about 3 times the standard error of the mean, which means that it's not likely due to chance. Okay, so that's how I look at numbers when I see them in an article. If I'm going to subtract them, I know the standard error of the mean is the square root of the two standard errors separately. So I approximate what the standard error of the mean is. I subtract to get the difference. I see how many times that difference is times the standard error of the mean, and I have roughly this table memorized, and so I can tell if the difference between those numbers is real or not. So that's what I look at when I look at data in articles. Now, if some people have fooled me by using standard errors, standard deviations here instead of standard errors of the mean, then I can't do this. And then I'm unhappy. Okay? And I do this when people present talks also. So I look for the size of the error bars on the graphs. And again, I'm unhappy if they've given me standard deviations, which I do many times, about a third of the time. More so from medical doctors. And then from the size of those error bars, I subtract out the difference, estimate the standard error of the mean, which I can do in my head, and then I find out whether the result is significant or not. So this is the procedure to go ahead and do this. Now we have two options here. We can ask two different questions. Question number one is, what is the probability that the z is greater than the z value of the mean? And so if I go back to the plot I was showing you before, this is the distribution. This was 6, and we got 6.7. I could ask, what's the probability that z was greater than 6.7? And this is called, because we're looking at one tail of the distribution, a one-tailed test. Now we could have asked a different question, which is called question number 2. Thank you. So in question number 2, we can ask a little bit differently. We can ask, what is the probability that Zm is far off of the theoretical one? Now what does far off mean? Far off means that Zm is either much greater than Z or Zm is much less than Z. So in this case, you can see that if Z was 6.7, we'd be too high. And if complementary Z was 5.3, which is the number I had before, we'd be too low. So it's only if Z was within this range that it would be kind of within the value we were expecting. And so we can ask not only, because we could have gotten a value that was too high, or we could have gotten a value that was too low. So if we ask the question that Z is basically different, Zm is different from Z, and this means that the Zm could have been greater than Z, or Zm could be less than Z. So we have to mirror reflect it around what the mean was, which we know in this case. And this is called a two-tailed test. And you can see that the probabilities, the p-value from a two-tailed test is actually going to be twice the probability from a one-tailed test. So now if I give, what I gave you before was the one-tailed test. If I now give you for a two-tailed test the z-values and the probabilities of getting z off of zm, either high or low, then these tables look like this: 1.6, 1.96, 2.6, 2.8, 3.1, and the probability values are 0.1, 0.05, 0.01, 0.005, 0.002, and for 1, 2, 3, 4, 5 in ZM, the p-values are 0.32, 0.05, 0.0027, 6 times 10 to the minus 5, and 6 times 10 to the minus 7. And you can see these values are just double the values I had in the previous table because we're looking at two tails of the distribution. So the question is, which one do we use? Do we use the one-tailed test or the two-tailed tests? And the answer is it depends on what we're asking. If we're asking are the z-values different from the one we know we're supposed to expect, then we use a two-tailed test. If we're only asking is the value we got in the experiment only high, then we use one-tailed, or is it only low, then we use a one-tailed test. So it depends which one we use. You can see in general we're going to get a higher value for the two-tailed test, which means it's less significant. Remember, because we're trying to keep that value small to see the difference between the experiment and the control. So that's the difference between one-tailed and two-tailed tests. Okay, maybe we'll take a break here until 10:30 and then we'll continue.